Hey, good afternoon, and thank you, Randolph. And please pass along my thanks to Jessica too for inviting us to present today. Really happy to be here. So yes, we're going to be talking about digital twins. It's sort of a buzz phrase these days when we talk about how to leverage analytics and things like AI and how can we turn those into business outcomes. So we'll talk a little bit about some of those case studies, and we're also going to dive into some philosophy about it and some lessons learned, and hopefully you'll walk away a little bit wiser. All right, so let's start off with what's going on in the world right now. Where is some of this discussion happening today as it relates to digital twins? Well, one of the areas, of course, is Seagray. Seagray is a great organization. If you're not involved in it, you really should be. A lot of great discussion happens there, but there's a particular working group there, the A2.65 Power Transformer and Digital Twins. And really, the point of this particular group is to say, hey, what is the reality of what we can measure and track on transformers that are in service or even in a spare yard? And what is the reality of what that data can tell us and what decisions we can make? And then we have to start getting into some of those more semantic types of conversation of, well, what kind of digital twin is it? What is it meant to do? Because we like the idea of having some sort of all embodied, super intelligent, virtual digital twin of a transformer that can really model or simulate almost everything. But the reality is it's just not true. And even if it was, you'd have to have the appropriate amount of data inputs to leverage that. So what's that gap? And then at the end of it, what kind of mathematical equations can we use? And we like to say manipulate, because really it's about torturing that data until it tells us what it wants to tell us at the end of the day. Now, Einstein has a great little quote down here. It says, as far as the laws of mathematics refer to reality, they are not certain. And as far as they are certain, they do not refer to reality. A little bit of a Schrodinger's cat kind of a discussion. So, I think it's definitely a good quote even to live by sometimes. So if we kind of this particular slide was taken as part of the working group for Seagray A2.65, and this is really kind of giving you a big picture of the overall discussions that are happening. You have a transformer; it's a physical asset. It has testing that I can do offline. It has testing or test results that I can monitor with my condition monitoring as well, and that data is available to me to make some sort of decision or some sort of model. Now, what I'm going to do with that data now is, well, I'm going to apply a mix of machine learning and analytics. We say here in the model that the model itself is, I like to say, it's first physics principles. We know that as temperature goes up, that viscosity of oil, for instance, will go down, which causes power factor and dissipation factor mobility to increase. Therefore, we get greater increases up and down. We know physically how that works. We understand the chemistry and the gassing rates that are generated within a transformer based upon temperature and or arcing. We can apply those, but now we want to add that next layer. What does it do in the real world? How does it react? And then we got to get back to what actions we want to do. So really, if you look at the kind of questions you have to ask yourself when you're exploring the use of a digital twin, is say, first and foremost, what decision am I trying to make? And I cannot stress enough how important it is to come back and ask yourself that question time and time again. And I'm going to kind of highlight this a little bit more as we go through our discussion as well here. So it's made by default, or is it by design? What am I looking at? What is that model? Is it performing the way it's supposed to? What is the digital twin made of? Maybe it's a collection of digital twins, twins of individual sub assets like load tap changers and bushings. What algorithms, what physics first principles, what machine learning algorithms are you looking at? These are all things that have to be done, but really, all of them really support almost that top question about what decision or what action that you're going to make. And you have to then start to look at the data that you have and whether or not it really is designed or can answer those questions. And if not, what level of confidence does it have? So it really is a lot to boil down when we look at this. So really, a digital twin, what is it? It's a model of a real physical object, but it is an abstraction. It's not the real thing. I think that people are learning that with AI and chatbots. It's not a real person you're talking to. So remember that, it doesn't have the same levels of empathy. Well, it's just a model. It just is trying to act like it's one, not necessarily be one for you. And you get that raw data that's going to come out of it. You're going to visualize it. You're going to look at it. And then you're going to look at your twin and say, hey, is this an evil twin? Is it not really going to help me make the decisions I think it is? Is it going to lure me into a false sense of security in using it? So again, let's take a look at some examples of digital twins. Digital twins, again, are just really, facsimiles of a real world model. A map can be a digital twin. You look at Google Maps, it's a digital twin. But we can see that if you were to try to use this particular map, it's a medieval age here, and you were trying to go between, let's say, Vienna to London, I think that the path that this map shows would not be very accurate, especially if you're trying to get, let's say, to someplace in South Africa or even South America. It's just not going to be a great digital twin. They can get better. That's why we learn. If you look at the map that Google Maps makes as a digital twin, if you didn't understand what decision it was trying to make for you and you were just walking in, you might look at that map and say, I now see that roads are blue between these two locations. Let us start to go and follow the blue road. That would be a very bad mistake, obviously. If you look at that distance between those two locations there, you were talking about over 1,000 kilometers. Well, how wide is this road? Is it several hundred kilometers wide on top of that, or is it that'd be crazy? Well, again, you have to understand what the business decision that you're trying to make from this map and perhaps this map before you even start to use it. And when you look at people, you look at utilities and you look at manufacturers as well as Doble engineering, where this is what we do for a living, is trying to model these types of activities, these types of assets. You've got to be honest about what it can and cannot do. And you got to make sure you're communicating to the entire organization what its intent is. Because one of the problems with digital twins, and back to that evil twin idea, is that once you're handed something, you might start to abuse it and use it in ways it was never intended to be used. So let's take a look at, we call digital triplets, or I would like to, it's kind of a little tongue in cheek, digital BFFs, or best friends forever. These are assets that are probably close in design. Maybe they're sequential serial numbers. Maybe they're in a similar family. And we're leveraging all of that data to develop our models. Well, Seagray has another group called the Dynamic Transformer Thermal Model that they developed. And here's kind of a visualization of what that looks like. And one of the points of this is to say, well, if I'm measuring a particular value over temperature, how much air could I expect to see? Well, if you were to take, and by the way, both IEEE and IEC have developed standards that discuss this. I'm sorry, it's a little blurred out there at the bottom, but hopefully the next one will pop up and you see it's 6076 and you see IEEE C57.91 there. This is telling you a prediction of the model of how much that temperature could vary based upon the temperature differential. And you can see here that if you look at this, well, it looks like IEEE might be a little bit more truthful. It's more centered around that 0-degree change than the IEC, which is a little bit low. Well, the data coming in that you're using for your model, well, here is the hotspot temperature, and we see actually a flip over of who you might want to trust a little bit more here based upon the study that Seagray did on this. And we can see in this case here that if you're looking at the hotspot temperature, well, IEEE is going to really have it all spread out there, and you see it's a little bit more compact than the IEC, and it's around 0. So both these models done by experts in the industry, and there's still just differences that you're trying to take into account for. And sometimes these models were generated during a time when, say, transformer designs, as we know, have become much more automated, a lot more compute powers going into them and designing and optimizing them. Some of the underlying fundamentals of construction have changed over time. And as a result, that's not captured in these kinds of first principle analytics. However, we can capture it in machine learning. But this is going to influence the ability for our digital twin to give us the right answer, because we're looking at air just based upon the models themselves. And if you look at a lot of models out there, models are usually a cascading set of models. One model feeds into the other, and they all start to compound their errors together. Then, of course, there's just noise on a system. If you're looking at, let's say, a sinusoidal wave that's coming through, say, a bushing tap adapter, and you're looking at it as activity, well, there could be partial discharge activity, corona activity, there could be power electronics, inverters functioning close by that's adding on to the noise of the system, or even just back channeled noise up to the ground of the grid of the transformer itself. How does that affect it? Now, if we look at that error and we said, let's try to model the error and see if we can undo the error. Well, there's a lot of work that does go into that. You could say, well, are we going to look at the mean error? Or am I going to look at the cumulative error? Well, you can see here the cumulative error goes up and stays up, but it looks like the mean is a little bit lower. What are you going to look at? How are you going to model it? That becomes part of the model, and that also becomes part of the error, though it could improve it, obviously. Now let's talk about the measurement device itself. And if you're looking at, and we're going to look at some examples of, say, look, you're doing an online DGA monitor. Now, DGA monitors use a variety of different types of technology out there. Generally speaking, GC or gas chromatographs are the most accurate, most like what you would go to a laboratory to do. And you look at photoacoustic methods, they tend to have lower and lower accuracies, but there's, of course, trade-offs, advantages, and costs and maintenance associated with these kinds of devices. But regardless, you need to know that, because that is what's going to go into your model, because your model may not have accounted for, let's say, the maximum errors in it before the numbers come out, or you just have to accept that error and what the actual output is. And we're going to get out to what that decision could look like. Well, let's take an example here of we're looking at a individual test result. We're looking at our different organic compound gas generations that come out, let's say, during a arc or thermal activity. And we're looking at here, we're in the D1 of a Duval triangle. I assume many of us here know what a Duval triangle is. I won't go into the details of it, but if you don't, hey, shoot me a text or an email and I can put you on some good stuff. But there's a lot of great information out there on what this can do for you. But in this particular, say, hey, it's low level, discharge D1 that we're looking at. But what happens as I start to apply some error? And generally speaking, if we're looking at error of a GC, around 10 to 15%. And again, this is us measured, what we're measured and seeing. And now we can see that we have a lot more results now are sitting in the D1, but there's a few now in D2, and there's a few more now in DT. That's that overlap of what's called a thermal style fault and a partial discharge or full discharge level fault that could be also acting together. Now let's go up to the highest levels of accuracy based upon the types of a DGA online monitor that you might select. And now we look at them and go, wow, there might be a more sitting in DT or D1. Maybe it's a tie. You now are starting to see that it starts to fundamentally change what the actual output, what the actual failure mode is, which would in turn probably change the way you're going to respond to this kind of alert that might be coming off of your SCADA system or your condition monitoring system directly to the utility asset owner. So again, we're looking at a span of that original measurement, put a little bit of error, some of the better ones on the GC levels, and that would shoot up to 30, 35% error. Again, it's going to change your response. And again, now take into effect that, well, perhaps I'm going to put that into a model. And that model now has to take into effect that it might have variation in just because for thermal performance that we saw, and let's say that Seagray paper that was published on the IEEE and IEC, that's going to now start compounding these errors. The other thing that you want to take into account is that you can create a digital twin, but digital twins, again, are usually a compounded or aggregated digital twin model of the main asset, the tank and the winding. The load tap changer might be included. It might have its own model that you're linking together in there. And then we have models of, let's say, the individual bushings. It could even include surge arresters too. Not likely, but yes, there's everything and everything tied up to it. You could include in that model. And we know that you can't just broad brush, how one asset from one manufacturer will perform versus another. So if you look at some cases where here we have like what's called a gradual rise in power factor. So by the way, this is a typical failure rate of the GE type U bushing that was probably all the discussion probably in the late 20th century and even into the early here, where they would slowly gradually get worse and worse until they failed. But then we have situations where, like a trench coat bushing, where just one suddenly goes up. Now it's suddenly in very, very dangerous condition. Your reaction to each of these cases would be different. Here's an example that came off of a generation company. And on it was, this is coming off of the generator, and you see all of these different measurements coming off of it. Now the question is, well, how are you routing that signal into your system? In the case of that happened here, it was going into a SCADA system, it was going into a model. However, when it wasn't probably used appropriately, because when this actually happened, this is where the alarm came in, as expected. They looked at it. Nobody knew what decision this was going to tell them, so they muted it, and they then did not take any action because it was muted. It was not going into their models. It was muted, and now the routing of it then was no longer responsive, and this did end up in a catastrophic failure that cost a lot of money to fix. Sometimes you're looking at, let's say we're looking at the 3 different bushings that on a transformer. We can see that we have normal levels here along the left-hand side. And it's going to, you see along here that one of those now suddenly just pops up a little bit. Now, one of the phenomena that you'll see in the way a bushing will react over time is that a layer will short, and you'll see an increase in power factor, and you'll even see the capacitance stepwise change. And then it begins to go up. And now the question is, well, what do you do when it goes to that level? And then what about the next level? And another question you might have to ask yourself is, those moments where it rose, the way it rose in that exact moment, that becomes also a factor in how you would look at that test result and say, oh, it didn't just gradually rise. It was a step change, and then it was steady. Step change, and then it was steady. I can't tell you how many times I've talked to somebody who said, Matt, the bushing went up a little bit, but it steadied out. It was okay. It was okay until it does it again, because it tends to start to get worse and worse and worse until eventually this unit did in fact fail. So here's another little cautionary tale about how you're going to bring this data into your model. So this is a case where we had, 3 bushings were being monitored, and on this graph, we're graphing not only the what's called the zero sum power factor, in other words, where you essentially just add them all together, and you get essentially, a relative version, and then you have what's called a true power factor. In this case here, we can see that both the sum current as well as the relative were rising together. And that really does help confirm to us, by the way, if you get into this kind of analysis, that it is in fact that bushing and not a combination of bushings. So if you were to see this over time, you might have a call out that says, when I go through my analytics, it comes out and I'm modeling how I'm going to, and then I'm going to look at my model, and then I'm going to put in my actions, my business actions I'm going to take. What do I do? Reach 1%. And hopefully you took those actions. Well, the customer was watching this. We looked at it and said, well, it's rising. It's rising. What should we do? He said, well, let's consider taking it out of service. Well, then the customer said, hey, you know what? Don't worry about it. It's fine now. Started to come back down again. Well, I like to say that, unfortunately, bushings are not bottles of wine. They don't get better with time. So what's going to end up happening is it starts to see this downward trend that's almost as cautionary. Again, your model sometimes doesn't know how to react sometimes to some of these kind of situations. So if you look at the way power factor or dissipation factor works inside of an insulation system, you're essentially measuring that angle between your reference voltage and the applied voltage, a current that's going through the asset. And that angle is the power factor angle. And that number is going to be usually a really small number based upon cosine of that number, which means you're probably getting something below 1%, very small, because that's, of course, the power transferring through the insulation, not down the transmission line. Unfortunately, there's a an effect that was documented many years ago, very famously by a fellow by the name of Dennis Kopik-Zinsky. And then another paper was also written on this by a fellow by the name of Long Fong, who works at Doble Engineering, that goes into this in much more gory detail if you're really curious about what is actually happening in this situation. But what in at a higher level is occurring here is that there is a lot of leakage. If you get a lot of leakage going to the ground flange of that bushing or inside that cap adapter, so much that it starts to, we'll say, overpower the measured signal, you'll essentially start bending your reference angle, which starts to make the power factor go low, if not negative. So people say, hey, I got a negative power factor. Does that mean my bushing is a generator now? The answer is no, it's not. It's probably got a lot of contamination or leakage somehow between the center conductor and somewhere to a ground if you're doing what's called an ungrounded specimen test, which is essentially what a bushing test is for those of you who are familiar with that kind of a test. Well, in the end, what they found out was that they were drawing samples that O-ring adapter at the very top of that bushing had become corroded and damaged, and the O-ring itself had become, water was ingressing into it, causing contamination to build up, a little bit of build up along the edges, and some overheating material was going on there as well, and that was creating that overarching value. So luckily, we did tell them that, look, it's not getting better; it's actually getting worse. You need to take it out of service and pull it out. And they did, in fact, pull it out. And yes, this was the case. And they were very pleased that in the end, it worked out for them. So what's the point of all this? We talked about models. Well, let's talk about one that is a lot of this digital twin discussion is digital twins kind of, again, they come in different types of business decisions and outcomes. And sometimes the decision is, I wanted to model the performance for, like, say, loading and things like that, things that are happening more real time, second to second. Well, asset health indexes are meant for those longer time spans, looking for strategic asset planning. What's my repair strategy? What's my maintenance strategy going to be over the next 5-10 years? And how can I prioritize what is there? So a digital twin that we use a lot in the industry is an asset health index. And we've built them into some of our software systems, like the Doble ARM system, as well as our fleet assessment services are using similar types of methodologies. But again, there's some good working groups out there and around the world that's really diving into this discussion today. But what an asset health index is going to condense all that complex data into a single set. It's going to make it so that you can look at it and make some decision. It's going to rank and prioritize something about the transformer. That something is, again, a maintenance decision, perhaps. It could be a repair, a maintenance activity I have to do. It's going to be supported by strategic asset planning, my CapEx and my OpEx planning as well. So it gets into the money of it all. It's going to drive my predictive and condition-based maintenance strategy, because I might use what's here as a decision about whether or not to invest more money into my condition monitoring strategy. And then, of course, finally, it's to provide a common framework for decision making. I'm going to put a big asterisk here. If you know what the decision was originally that you were designing to, and it didn't get lost in all of the cacophony and discussion that were happening over time. So let's take a look at an example of how you might do an asset health indexing. This is actually a real case here. So we're looking at where this particular customer is using a 1 to 5 ranking, and they were ranking all the individual systems within the transformer about what its condition was. And they wanted to then model a health index, their digital twin, for the overall long-term condition of that asset. Well, here we got 2s, 1s, and so it looks about average, above average. Well, let's take a look at 2 more transformers, that were next to it in the same yard and how they did. So the question is going to be which one are you worried about? So are you going to look at the one that's got the highest numbers, the biggest average? Well, let's take a look at what that looks like. Well, now the subject matter experts went in there and weighted on the score, and they said, hey, this is a 3, that's a 1, that's a 2, because I'm looking at the numbers, and the big picture is this. If you sum it together, they're looking like they're in a dead heat. And again, the normalized sum is showing the same problem. The one you should be worried about is the 5, because that's what's going to take the transformer out. That's what's going to fail the asset. Yes, the rest of it's probably in pretty good condition, but it won't be if it's on fire. So you have to, again, ask yourself, what's the decision you're trying to make? Are you trying to provide a very big general number, or are you trying to use it to actually prevent a failure, uh, or perhaps another, again, a maintenance activity or a replacement program? You got to look at that all. Here's an example of a scoring system that was used that in the end, they would want a utility. This is actually National Grid. They had a 1 through 4 ranking system, and again, it's important that it has a time based system, an AI based on a Delphic system. And this was just 4 codes, very simple. What do I worry about? What do I not worry about? 2 to 5, 5 to 10, 15, maybe. Do it after that. Well, you can revise it. Your digital twin can be, that's my, if you see the upper hand corner, that's my one did with pencil. You can get more and more exact over time. And again, you want to get more specific. The more specific you can get about the system and its outputs, the more specific you might be able to get about how you make that business decision as well. So again, this is about learning about how to use it as well. Let's look at another case. Again, this was from National Grid. And we're looking at after they had used that same exact system 1 through 5, and again, we're using our expanded one that we showed there last. We can see that before scrapping, this is what they predicted it would be, that the overall health that they would see. Then they went in and tore them open, looked inside, and said, all right, let's validate our model so we can actually improve our model. And you can see overall, this looks pretty darn good, right? It's not too bad, for something like this. Well, let's go to the next 7. Well, it doesn't look nearly as good. It looks like there was a lot of variation in it. And again, you just got to take that. And what's the reason why? Well, I could go back and review the first 5 or so slides, but it's all of those errors and understanding in physics first principles and the asset in question and how it performs in relationship to another manufacturer. So before scrapping, you can see what it looked like. Very similar case, except for that 4 on the right-hand side. And after scrapping, we can see that, yeah, we got 7 out of 14. So is that good? Is that bad? That's eye of the beholder sometimes. There was a flight surgeon. Her name was Harriet Hall, and she did a funny study. Actually, there's papers written on this that she put together about tooth fairy science. And she said, nobody's ever studied how to maximize or how much money somebody gets when they lose a tooth. Do they get more if they put it, more? Do they get more cash for the first tooth, the last tooth? They get a plastic bag. What if the kids swallowed the tooth? That's happened several times at our house. So we had to wrestle with that, or made a really good story to cover that situation. Well, we have to have, of course, good data. It has to be reproducible. It has to be statistically significant. That usually means I have to have a data set that I can trust to give me at least a semblance of a good feel for what that particular thing I'm studying is going to do. Well, she said, at the end of it, that yes, you have learned something, but you haven't learned what you think you have learned, because sadly, there is no tooth fairy. In other words, we can model anything we want to, but at the end of the day, the question is can I actually use it or not? And is it going to actually provide feedback to the end user in the end? If you can't feed it back to the kids, let them know, hey, next time you should make sure you put it under the pillow in a silk bag, you'll get more money. They're not going to be able to take advantage of it. But unfortunately, of course, it's not going to help them at the end of the day. Let's talk about a recent case that happened. I'm sure everybody remembers the London Heathrow incident. That is where the London Heathrow went down for quite a long time and made all the news. And I'll say that Doble was actually on the ground pretty quick. Doble Engineering was on the ground pretty quick. So we're going to look at the London Heathrow, the substation that was close to it, that was part of it. And this is a side view of 2 transformers, SGT1 and SGT3. Now, if you look down on top of the Heathrow, the London Heathrow substation here, you can see those 3 transformers. The area in green is the neighboring distribution company. I think it's Southeast Electric there outside London. And there's of course, the one that we'll be looking at this 275 kV side. So here is the sequence of events. On May of 2012, they had 8 parts per million of moisture. Take a real quick sip here. And then in 2008, they got a 48 part per million moisture notice from the transformer. Now, the NGET guidance for that's the National Energy. Forget the name of it. It's their organizational body there in the UK. States that moisture at this level indicates an imminent fault and that the bushing should be replaced. It's a category 1 that was set in their procedures for NGET. Well, unfortunately, they took no action because this was a category 1. And the question is, well, how many category 1s did they have that day in their system that was modeled up to be a 1? 60. So it was 1 of 60 super high urgent alarms that were going off. And, one of the sayings is that everything is urgent, then nothing is. Unfortunately, you kind of fall into that trap. So again, it may be a great model. It may provide a great linearity or representation, but if it's not actually matched and calibrated to the decision you're making, it's not going to help out. But they had a lot of priorities going on. And unfortunately, there's something that was missed in this whole discussion was, there was a concern that the asset was in imminent danger, but what was the consequence of the failure of that asset was not truly understood at this point. Because, engineers we get kind of focused on the data and we are making a decision about that case there without the big picture involved inside of it sometimes. Well, in 2022, they deferred the planned maintenance again. It's things are busy. It was 2022. They planned the maintenance on SGT3, and unfortunately, again in March 23rd, they deferred the basic maintenance again after a change in policy, but the historic bushing data was not reviewed. In other words, they were reviewing the transformer, but not the bushing. Because remember, we talk about how models are sometimes compounded models on top of each other, and that was just not considered, unfortunately, in this case here. SGT went end of life with a score of 12.7. That means that it wasn't that old in score, but unfortunately, the bushing again was not included in the end of life scoring that they were doing for trying to predict how long that asset would last. Well, you can imagine that the result was far from ideal, and it ended up the bushing failed. So if you look at the situation that was going on, this is Heathrow, and they have these 3. Unfortunately, a lot of the switching was pretty much a manual switching event. And if any one of them had gone down, they would lose power to the airport the way it was set up, and had to be a manual transition to do so. And that was one of the reasons it took so long to bring the system back up. So the question is that National Grid was, what do we know? Well, they know that if they lose one of the 3 independent sites, it would result in loss of power. And maybe we should have thought about that. Maybe we should have talked to the distribution side also, because there's another customer involved. What they didn't understand was the consequence. What was going to happen if they had lost it? And in this case here, Heathrow chose not to invest, unfortunately, $1.2 billion to address the risk. And I think that I don't know what the end result of all the monetary values are, but at the end of it, but I'm sure it's a rough system to discuss. The IET did the investigation, the Institute of Engineering Technology, and they said that there was critical weaknesses and faults in the system management, maintenance regimes, and cross-sector coordination to protect essential infrastructure. And interestingly enough, they said on 3, using technology like digital twins can help us create models that identify potential problems in a virtual environment, allowing us to solve them before they occur in real world. Now, I have to say that I'm not completely sold on this last statement because, again, a digital twin doesn't solve the problem. The algorithm, the machine learning, the model, and what it's intended does it, not just the idea of running to a digital twin. It's complex behavior. I always say transformers are living and breathing. No matter what you may say, I think they're conscious sometimes because they have a lot of the. I always say it's as complicated sometimes as analyzing the human body whenever it gets down to some of the interactions that can occur inside here, and you need to have people involved with that review. So what was the recommendation that came from them? Well, they said particular attention should be paid to any area reliant on manual controls. So they had to look into automation. They said asset owners should review the suite of mitigating actions to deployed, because again, were the actions properly set up? and what considerations will be given to the use of the most up-to-date technology, including digital twins. And this is, of course, something they started to get into. And by the way, as I mentioned before, though I cannot share the internal reports confidential, Doble Engineering did do the forensic analysis in this case. And yes, it was moisture ingress into the bushing, just like that article said. I'll tell you, it was a surprise to us when we found out that the news article came out and had our name on it, because we weren't told. We were being very quiet, but our phone lit up that day. So, and I'd like to just summarize by being a little bit philosophical here toward the end. We all know about the Dunning-Kruger effect, which is the more you know you don't know. Unfortunately, the converse can be true. The less you know, you actually think you know more. All right, so we call that the peak of Mount Stupid. Now, when you finally figure out you don't know anything, that's the valley of despair. That's your first year college in electrical engineering, and you hit your first physics and electrical engineering circuits class, and you're like, oh dear goodness gracious, I'm really stupid. But then you start to figure it out, and you never truly probably get all the way up in confidence that you had probably beforehand whenever you were doing, let's say, that Radio Shack circuit project. For those of us who can remember going to Radio Shack and buying circuit toys to play with and build, you realize that, I didn't learn everything back then with those circuit board kits. I actually have to go to school and learn a little more, and there's a lot to learn. People with a little knowledge usually have overconfidence in their ability. And of course, that's the Justin Kruger and David Dunning put that out for us. Well, unfortunately, AI is right now, and AI and machine learning, I kind of lump them together and how they fit in the digital twins. Of course, everybody's talking about how they fit in the digital twins. We have to be careful of the Dunning-Kruger effect, where we think that we're suddenly experts because we have asked, let's say, a chat bot or chat GPT, or you ask Claude a question and suddenly you got an answer back and you're talking like you're an expert on the subject. Well, talk to a subject matter expert and they will start to poke holes in the little things that you are not aware of. And with the dangers of these types of digital twin models, or any type of system that's going to give you hey, this is a great shape, or no worries, do it in 15 years, is, are you actually checking it? And if you don't have experts who can judge and validate it, you're probably going to be in trouble, and you're going to be ending up with an evil twin at the end of the day. So what's changing in the world of digital twins? What are we working on? Well, again, proliferation of AI machine learning models. I mean, at Doble Engineering, we have what's called the Doble database. It goes back to the 1930s. It's millions. It's like tens and tens of millions of data points are in that database of assets that span, some are been in service for over 70, 80 years. And we use that to do our machine learning or statistical analysis into our analytics. And we've also used machine learning to build out some of our online condition monitoring tools, be it pre-built condition monitoring, where we learned on other systems like a digital twin's best friend, or on the unit itself. But now we're notching those things up because the technology is just getting more accessible and easier to use. People are looking to automate health indexes. They're trying to automate the actions based upon health indexes. They're trying to get quantitative in these outputs, much more precise, and they want them to be authoritative. That's the dangerous word there. Here's the hidden problem. They're complex. They're not easy. It's got thermal modeling. The type of oil being used can change things around. The appearance of contaminants, moisture can change the physics in and of itself, beyond just increasing or making test results worse. It doesn't have the subject matter experts' nuance, understanding what that means and what the consequence is. But they're harder to understand versus a simplified output. So people will always want to fall back. And unfortunately, the Dunning-Kruger effect is going to become a problem. We have to make sure, again, what is the decision you're trying to make, and can it make it or not? You have to know that question again. So we have to have the SME in the loop. You hear about the human in the loop? Well, I like to say the SME in the loop sometimes. The SME, what they actually do is they're looking at the failure mode context, the mechanisms. What are the notices coming out from vendors? How does that affect it? What's the data quality? Does my model, is it able to recognize if communication was lost, or let's say it was suddenly put in maintenance mode and the number just turns to a -1 for some reason. Can it recognize that? This is stuff that you just can't capture completely sometimes, these types of models. What's the boundary conditions? What's the probabilistic judgment of the risk and how that relates back again to the final thing? What if you don't have it? What you're going to do is have a misinterpretation of the athlete health index. You're going to start using it for things like condition monitoring scoring, alarm. Hey, your health index has gone up by 5. Look, if you're trying to make a condition monitoring system out of a health index, you're probably going down the wrong road, because you're taking a number that was probably meant for strategic long-term asset planning and trying to create it into a short-term number. You're going to start to overtrust it, and you're going to start to get model drift because it's garbage in, garbage out, and you're not reinforcing the right things. So respect the digital twin. You got to understand what it does. It's going to generate some insights. Keep your SMEs right at hand. Yes, they can use these tools to make themselves more, more proficient and to expand what they can review. But at the end, they still have to understand what the models do and how they work. And they have to have a way to feed back the results. There was an excellent paper written by the late Tom Rhodes from Duke Energy, where he had talked how much work went into some of their analytics and machine learning, and how they had to institute into their business processes the ability to review and feedback. That is part of building out these kinds of systems. So I hope that becomes something that you can think about and take to heart. And with that, hey, I appreciate your time today.